But let's get on with this morning. This morning I'm going to be doing an introduction. I'm basically going to be summarising a lot of what we've said in 2019 presentations and just giving you a bit of an update on where we are with some of the developments since then. I'm not going to read all of these, but this is an extract from the front page of the EMC part of the technical part of the website. And it gives you there links to help you find interference, gives you some advice on how to not break through, gives you lots of papers that have happened in the past on EMC matters. There are 15 different detailed leaflets which can help you solve your EMC problems. We also run a help desk, and the address for it is there. But our sort of forward-looking work is mainly to do with protecting the spectrum from RFI. We have a number of investigations, which we can tell you a lot more detail about this afternoon. We also do a lot of work on the standards committees, both on EMF and EMC. And the EMC committee took on the lead, although we formed a separate team for the EMF work. So if you want to find anything in the way of advice, go via that web page, click the links and you'll get there. Now next, I'm going to give you a quick look at the outcome of some of the stuff from the help desks. We had 52 reports so far this year. Interestingly enough, the majority of them were saying, how do I find the source of interference? 21 of them. And then a few people who got a bit further on, you'll notice that solar PV is fairly high up the list. So there were two common items in those reports. One was more advice was needed on how to locate and identify causes, and I'll talk about that in a moment. And the second one was the majority of the RFI is caused by switching systems, either small SMPSUs or high power around solar systems and that sort of thing. It's basically when you're trying to convert AC to DC or generate AC from DC. And as we're getting more and more offshore farms carrying huge currents back into the grid, we are going to be suffering more and more from this in the future. And more locally, of course, the little switch mode power supplies, a lot of those are very noisy. And also with electric vehicles, they've got to be charged. They're all giving you lots of square waves, lots of square waves, lots of harmonics. So what is electromagnetic compatibility? It's basically the ability of two items to work together without interfering with each other. So here you see a source and a victim. And there are two main methods of energy getting from the source to the victim. One is radiated emissions and the other is conducted emissions. Now with the conducted emissions, just put the pen on. You can have straight ohmic conduction, a wire between the two, or you can get coupling. You can either have inductive or capacitive coupling. And the job of us as amateurs, having got equipment which hopefully has passed these EMC tests in the first place, is to set it up in such a way that we minimise the impact of ingress, which is people interfering with us, and egress, which is us interfering with them. So let's assume that we've got that understood. You've got a source of radio frequency interference and you want to find it. What do you do? Well, in the early days, we would have said, pick up an old analog radio. We heard this morning that there's less and less analog around since 1999. And go around looking for 50 hertz hum or 100 hertz hum. Still do it, by all means. You can pick these up for a few quid. It's the cheapest way of doing it. But if you want to get to something a bit more complicated, then what you need to do is first of all to know what you're looking for. I don't know if you've ever answered the request of, where is that thingamajig that we had sometime last week? If you don't know what you're looking for, you're probably not going to find it. So know what it looks like or what it sounds like, and then go looking. Beforehand, you can probably save yourself a lot of time by making sure it's not something in your next room. So turn off the part of your property, make sure it's not you. If it is you, turn it back on one at a time, note when the power interference comes back again, and then go and find the equipment. You might want to check with a different antenna, because the ability to pick up noise interference is quite different between electric field antennas and H field antennas. Check a little while away. I've had people who I've been helping over the phone who've been chasing Radio 5. Go a bit further away. If it's still there, then it could be a real transmission. Log the times and work out what it might be from when things might come on and off. Listen or use an SDR to find out how extensive it is. And there's a specific leaflet, EMC 04, which you can get at via the leaflets part of the website that tells you how to do that. And when located and you think you know where it is, then use the on-off-on test. Anybody know what the on-off-on test is? It's quite a simple test. If it's there when something's turned on, turn it off. If it goes away and when you turn it back on again, it comes back again, you found it. So that's the on-off-on test, which is all you really need to know if you can actually get to the breakers to do that. If you can't, and you need to go looking, then I've got two examples here, and we'll be demonstrating both of these this afternoon. But basically, with a little loop, which we'll show you how to make in a minute, you can either connect something like an RSP1A or whatever SDR you have in your shack. RSP1A comes with a spectrum analyzer plugin software, not a plugin, sorry, software. And you can hook that up and you can go round and you do two things. You're either looking for proximity, which is as you get closer the signal gets louder, or you can use it for the H field with a loop which has sharp nulls and you can work out which direction it's in. With the combination of those two, you can probably get at most things. And as I said, we'll have these this afternoon set up with a noise source, and we can show you how the different ones work. Starting with the simplest thing, the difficulty with that is making sure that you can get sufficient signal. With some of the simpler things, like the RF Explorer, it's got an LNA in it. But with the next one, which is a tiny spectrum analyzer, you have to be much closer to the source because the sensitivity is lower. And what I've shown also on here is a couple of E-field antennas, one made out of a patch antenna that you can buy, electric field antenna, via the famous web or Amazon, and the other one is a HUP RF one, which you can still get. But the tiny SA does need an active antenna. If you want to make one of these, and here I've just pinched the work of Ian Miles because it was a great paper that he did in Radcom in September 21 when he actually went out and found the source of interference himself. And you have to admire him. Basically, to make the loop, you take a bit of 239 or any of the other types of feeder. You cut a 20mm piece out of the outer jacket in the middle. You have a normal connector on one end, and then you butcher the connector at the other end. So you have a normal connector here. It's not showing up. You have a normal connector on the right, and on the left you take the pin out of the connector and you short the center and the braid together. Use a T-junction to get that to your system, and you end up with something like that. This is made out of normal coax, and you can, but the thicker one, which I've got in the bag, is easier to use. Now Ian decided the best thing to use was his own radio, so he stuck a rucksack on his front and he shoved in it a 991 and a 12-volt battery, and he wandered around the district with that. And he found his interference, which was a Fox Sewer battery charger. Great job. So in summary, if you want to locate the source of interference, you need something like I've just described. Use a small loop to DF the null. you beware of finding near-field sources. The first thing that anybody does, particularly with an E-field antenna, is they find about 1,000 sources from just about every piece of equipment, because the E-field antenna is in the very near field. So you need to find out that your source that you think you found is going down a bit more slowly than they will do for the near field. Check the signature so you know what you're looking for. For distant sources, use triangulation and try to identify the signal. If it's a real signal, there is a website called SIGID Wiki which gives you some of these signatures for real signals which you can use to find. So quickly, once you've done all of that, the other thing that you should definitely do is to clean up your shack. So how does RFI get out of my shack? And I thank Ian, GM3SEK, for these slides from his 2019 convention talk. There you've got a typical transceiver, power meter and matching circuit connected via a feeder to an antenna. If the feed line radiates due to common mode currents, that will be one source. The other main source of interference is into the mains. You get RF in the shack problems, your feed line is radiating and you're transmitting RF into the mains. How do you fix that? Very, very simply, with a few ferrites. To stop it, stop the stuff with a ferrite choke at the feed point, choke balun, stick another one on the input or the output of your antenna tuner and put a mains choke box on the mains. If you do that, you'll stop most of the interference getting out. But fortunately, your shack is now clean, you're not transmitting into the mains, you've got reduced radiation, and strangely enough, if you look at where the interference comes from into your system, it either comes from the mains, which gets into the shack, flows up the outside of the coax, gets coupled back into your antenna. So the solution for stopping RF from getting in is exactly the same as it was to stop it from getting out. We've got some of the chokes, and we will have for you to look at this afternoon Ian's excellent mains filter, which cleans up the main supply in your shack very well. One thing you do have to be aware of, though, is if you plug something in on the clean side that is dirty, like one of my old computer power supplies, my laptop power supply, it was still getting in because I was inside the clean area. So beware of that. Solar photovoltaic cells, you can get lots of radiation from the various parts of the system shown by the red lines on there. The optimizers, which are connected to the panels, they're DC to DC converters, and they are the square wave on the power supplies. The inverter needs to communicate with the optimizers, and it does this in such a way that it can sometimes generate radiated emissions. Some systems have MPPT, and this on the DC input can cause interference. Now, I've taken this from David's excellent article in the most recent RADCOM, and he will be able to tell you this afternoon about the work he's been doing on solar PV. This is another more typical system. There are certain recommendations that are made by the installers to help prevent interference. Keep the battery leads short, twist them together, daisy chain the wiring between the panels, put in screening where it's needed, stick ferrite cores everywhere. And what David says is most important is to make sure your inverter complies with that standard, 55011-2016, because that will help to make sure that you've got less problems. We'll also show this afternoon the famous Foxhill battery charger, and David will have it set up showing conducted emissions, and we will play with some of these tools to find radiated ones. So that's part of the demonstration for this afternoon. The last thing on the EMC side that we'll be giving more detail on is the IARU noise measurement, noise floor measurement, and David again is the main contact for that. We're also fortunate to have John, who's got a lot of experience from the other side in that area, and he'll be happy to talk to you about how we can help you with EMC problems. But also here to talk about EMF, give you an introduction to that. So assessing your station against Ofcom compliance limits. I guess you've all done that, haven't you, because your licence requires you to?
Yes, sir.
Good, well done. Let's just see what it means. That's a little diagram which I think helps summarise the problem. We all know that for an inverted V type antenna, then the voltage nodes are going to be at the bottom, and if you get them close enough to the ground, you're going to have hot spots where the limit will be exceeded. As you change the frequency, those hot spots will move around. So what we decided to do to be safe is to define the amber rectangle as what we call the exclusion zone. So as long as nobody's in that area, then you can't subject them to emissions that are above the limit. The green area is the area where you can do what you want. Anybody can be in there, there's no problem. And what the EMF regulations tell you need to do is to make sure that there's nobody in the exclusion zone where exposure limits may be exceeded when you transmit. So if there's nobody in the exclusion zone, you can transmit. If they are, you can stop transmitting, shift them out and start again. Or if they're going to be there for a long while, you could do something wonderful like turn the wick down such your diagram says it's not an exclusion zone anymore, and then you can still transmit. So one of the things that we were faced with at the beginning was everybody getting very, very worried about whether they could comply. Most people who've tried can. How many of you have let's just look at what you have to do to comply. Do you need to comply? Yes, it's a license condition. You need to carry out a compliance check, and there's different ways of doing it there. All you need to know is your basic station parameters for all of the methods. The methods will do all the hard work for you. You can either use a calculator, or where we've done the work and come up with pre-assessed equipment configurations, stick with one of those and quote that. Or the work we're doing at the moment is where there are areas of uncertainty in our minds, we use modelling or measurement to determine what is really happening and if more help is needed. Once you've done that, define the exclusion zone and how you're going to police it, how you're going to stop people getting in there. And the last thing you must do is keep a record of what you've done, because Ofcom will come along and say, show me, not go away and do it. They'll say, show me. How many of you used the calculator app? Most of you? How many haven't? Do you still transmit? 2, I think. That's amazing. In a room of this size, we've only got a couple of people who haven't used it. Well, all you basically do is in the left-hand column is you feed in your station parameters, like your band, your mode, your feeder losses, your antenna gain, and it calculates the average and peak power, and if you need to, it will tell you what your compliance distance is. Now that's a very simple calculation, and to make sure that it doesn't give an unsafe answer, it tends to give you a bigger exclusion zone than it actually is there. For some of the types of configuration, will give you a much more detailed plot of where the exclusion zone is, where you can and can't go at ground level, and where your main beam would be if it was pointing in that direction, which is the yellow piece. And the orange circle at the bottom of that diagram is the up to that height, you are not in a problem. It will also tell you what height you need. It does it to 2 different limits and to other methods that we've done. And it allows you, if you want to be a little bit more clever with the simple calculator, to say, well, I know my beam is pointing over there. I know that where that guy in the front row is sitting is 6 dB less, so you can put in the directivity factor and give yourself a bit more distance. So how do you use the results of that calculator app? And I should at this stage check Ollie Stum, who wrote an excellent piece of software. I had a funny spreadsheet version in the early days, if you remember, while we were working it out, and he took it all, automated it on the calculator app. And we're now getting requests from other countries if they can use our app, which is a great testament to the hard work of the EMF team and the international team. And I see we're joined by our keynote speaker, Raphael, who joined in to that group. And it's been a great experience, great fun getting there. So how do you use the results? It computes a compliance distance, which is a minimum separation, and it helps you determine the exclusion zone. You need to ensure that no one is present in that. I've said that a few times now, it's because it's important. Nobody's present in that EZ when you're transmitting. If the EZ is close to accessible area, what's an accessible area? Somewhere where people can be, where they might commonly walk, or where you can't see where they are. So if there is an accessible area close to the EZ, we recommend you move the exclusion zone a little bit. You can do that by raising your antenna or reducing your power. Turn the wick down a bit. You can take practical, if you don't want to do that or you can't do that, you can take practical steps to manage and or monitor access, like closed circuit television cameras or a fellow amateur sitting out there with a book keeping a check for you. You can use the results from the calculator to judge what would be most appropriate for you to do to manage your exclusion zone. And I think I've said this a couple of times already, quite deliberately. Remember, if you can be sure no one is present in the exclusion zone, you're always free to transmit. Believe it or not, if there's nobody in the exclusion zone, it's not a problem. Pre-assessed configurations. This is a lot of work that's been done by the team. I'm just going to outline it, whet your appetite a bit. We went into this in more detail in the 2022 convention, but unfortunately it didn't get videoed. At the top there we've got half of a 40 metre inverted V and the patterns as to where the exclusion zones would be for different power levels. We recommend that we simplify that down to rectangles because the position of the hotspots, if you remember, moves with frequency. Having simplified it down to rectangles for different power levels, we can come up with some simple recommendations like at 10 watts, 0.5 of a metre separation, 100 watts, 1 metre, 400 watts, 2 metres. And then you get down to that diagram that we started off with. Determining and managing the exclusion zones, find the accessible areas, work out the compliance distances, work out where they overlap with the exclusion zones and record these, and you're done. All right? If we do need or we want to measure, then it requires specialist equipment. We have two types of equipment we've used, the Roden Swartz and the NADA. And what these basically do is they measure the E and H fields in 3 dimensions, X, Y and Z, and then they calculate the mean and peak power and various other things and give you a reading. So we got together with Ofcom as we both needed to solve the problem of how to measure EMF, and we went out and measured some antennas. We deliberately chose what I call compromise antennas. Those are antennas that have got traps or are not the right size and therefore likely to have some strange field patterns. We set up the probes. We use low power because we use 1 to 4 watts, which means it's safe to do the test, and also it doesn't interfere with other people. The field strength scales perfectly with the square root of the power. So, you know, if you measure at 4 watts, you want to know the 400 watts, you just multiply your results by 10. We did the work at the resonant point of the antenna, the lowest VSWR in the band. We laid down a marker 2.5 meters away because during the evolution of this work, we worked out what we call the 2.4 or the 8-foot rule, which is make sure your minimum compliance distance is more than 2.4 meters. Why is that? Well, you have a requirement to make sure people can't touch it as well. And you can't, if it's 2.4 meters away, touch it. So we laid down test markers. We then went up and down with the probes, found the peaks, and then did measurements at different heights and compared that with the standards. We made the measurements at 8 different heights, but we only made it outside the recommended limit of 2.4 meters. Why do we, although there's a good reason of not being able to touch it, having started off with the measurements, once you get inside 2.4 meters, you only have to have a blade of grass move and the meeting moves. So it's hopeless, it's a waste of time. The other thing you have to do, particularly for E-field measurements, is make sure you're 10 meters away or 5 meters away, because if you have somebody walking about while you're making the measurements, you can actually see the measurements move. So measurements are quite difficult and not to be recommended, except for trying to find out areas that it's difficult to really be certain about the modelling. This is some work I did with a loaded dipole. It doesn't show up very well there, but it is a loaded dipole up in the air. And basically, we worked out a method to present the results. All you need to know is that if it's not red, then it's compliant. If it's red, it's not compliant. And if it's yellow, then it's getting marginal, you know, around 90% compliant, but only just. So for 400 watts, at 2.4 meters height, this was slightly non-compliant for being less than 2.5 meters from the antenna. But we recommend that you're at least 2.4 meters away, so there's no problem with that. We did a similar thing for the vertical, and if you went to 1 kilowatt, then the 2.4 meters would become 3.8 meters. We don't need to measure it again because it scales with power. And we did check that it scales with power with our test method. For the vertical, this is a trap vertical. We did a similar thing. I just want you to think about the shapes of the curve. That top curve in blue is because you're getting closer to the antenna, the kick up at the top. What's the bottom curve doing going in the opposite direction? Anybody got any ideas? So we get closer. Well, it's because you're getting closer to the radials. The radials actually transmit as well. In fact, when I was doing this test, I couldn't remember where I'd put my radials down. And I wanted to measure above and not above the radial, so I just went round and measured where the field strengths were near the ground and tracked out where all my radials were, and then I could do the test. And in fact, recently, in some work that Peter will show you this afternoon, he's done some modelling which shows exactly the same thing, that you need to be aware of your radials. And our recommendation is that you stay at least the compliance distance away from any active part of the antenna, and radials are an active part of the antenna. And basically, for up to 400 watts, you're fine. 1 kilowatt, if you've got enough space, you're okay, but you can actually get close to the reference levels, the limits, with 1 kilowatt, so beware. So we recommend that you do a bit more thought in that circumstance. We produced all of our EMF work and kept it on the EMF part of the website. There are 3 excellent papers there, EMF 1, 2 and 3, which the team produced. EMF 3 is a new one that we snuck in there, and it comes to a point that Raphael made in his keynote speech, that the way you deal with your neighbours is important. And the international team that's been working on this produced EMF 3 with just a little bit of help from Peter and Ian, who wrote most of it. And that I do recommend that you get on and read that, because if you do have any problems with people saying, but you're going to zap me from your antenna, that gives you a lot of useful advice. And there are similar advices on EMC. We've got 2 pre-assessed equipment configurations up there already for half-wave dipoles and for rotatable beam antennas. And there's some provisional microwave advice pointed to, which was work done with PAECs. So, please come along this afternoon at our clinic and tackle us about EMC and EMF.